Welcome to This Explainer. Today, we're tackling a foundational concept that literally separates good programmers from truly great software engineers. I want you to imagine, just for a moment, that you have two programs sitting right in front of you. Both of them solve the exact same problem, and both give you the exact correct answer. But there's a huge catch. One program flashes the answer on your screen in a single second. The other one? Well, it just grinds away, locking up your terminal for a full 10 minutes while you sit there questioning your life choices.
So, which program is better? I mean, it's a total no-brainer, right? The faster one, for sure. In the world of software development, faster is almost always better. And this massive difference in execution time brings us to the ultimate metric for algorithmic success: time complexity. If you're looking to ace coding interviews at places like Google, Amazon, or Microsoft, this is absolutely crucial to understand.
Okay, let's dive into this. Here's our roadmap. We'll be going over the cost of slow code, decoding big O notation, looking at best, average, and worst-case scenarios, scaling for massive data, and finally, tips for code optimization.
Section 1. The cost of slow code, measuring performance without hardware. To really wrap our heads around this, we first need to separate your code's efficiency from your computer's sheer processing power. Time complexity is simply the amount of time an algorithm takes to complete as the input size increases. Basically, it measures how fast or slow your program runs, totally independent of your hardware. Think about it. If you've got a list containing just 10 numbers, searching through it is going to be incredibly quick on almost any machine. But what if that list contains 10 lakh numbers, or a million? Suddenly, that running time just spikes. Time complexity lets us analyze this performance drop logically, telling us how an algorithm behaves when the input size becomes genuinely massive.
Section 2. Decoding big O notation, measuring growth. So this is the underlying theoretical framework we use to actually measure algorithmic scale. Big O notation is literally the mathematical language of time complexity. It describes how your running time grows as the input size, which we usually just call n, increases. Imagine your input n growing from 10 items to 1,000 items. Big O is how we measure that resulting explosion in execution time. It basically maps out the trajectory of your code's performance. Now, what's really interesting about this slide is how we categorize this behavior. First up is O of 1, or constant time. Imagine this as a perfect flat line on a graph. Whether your array has 4 elements or 40 lakh elements, finding the first item takes the exact same amount of time. It's incredibly efficient. Then we have O of n, linear time. This one is kind of like reading a book. If you double the pages, well, it takes twice as long. The execution time increases directly with the input size. But as we move further down this list, things start to get pretty dangerous. The danger is really in the data. If we have an input of 100, an O of n linear algorithm takes 100 operations. Makes sense, right? But an O of n squared, or quadratic time algorithm, absolutely explodes to 10,000 operations. Quadratic complexity usually happens when you use nested loops in your code. As your input n gets larger, the number of operations doesn't just grow, it compounds aggressively, turning your code incredibly inefficient real quick. So let's anchor ourselves on this visual spectrum here, going from fastest to slowest. We already know O of 1 is our constant champion, but look right beneath it at O of log n, logarithmic time. This is a real game changer and considered one of the most efficient complexities possible. A great example is binary search, which practically halves the problem size step by step, instead of checking every single element. You also see O of n log n, very common for efficient sorting algorithms. But at the very bottom, no way around it, O of 2 to the power of n, exponential time. Think of unoptimized recursive Fibonacci algorithms. It is cripplingly slow for large inputs. Section 3. Best, average, worst cases, measuring reality. You know, in the real world of software development, we don't just get to look at one perfect magical scenario. Take a standard linear search. The best case is the minimum time required, you get super lucky, and the item you're looking for is right there at the very first position. But the worst case is the maximum possible time required. The item is buried all the way at the very last position, forcing your program to check literally everything. As a programmer, you absolutely must anticipate this worst-case scenario to accurately judge how your app will hold up under pressure. Section 4. Scaling for massive data. The macro problem. Let's zoom out from the micro algorithms to the monumental scale of global platforms. Just think about companies like Google. Amazon, or social media giants handling millions of users every single second. Google has to deliver search results in milliseconds. Amazon is constantly sorting through millions of products. Social media apps completely rely on optimized recommendation systems to feed you content instantly. Without highly efficient algorithms, these modern applications would suffer from completely frozen apps, agonizingly slow searches, videos that buffer endlessly, and ultimately crashed servers. To put that into perspective, Amazon once found that just 100 milliseconds of latency cost them a full 1% in sales.
So the crucial point is this. Top-tier companies care deeply about time complexity because it literally impacts their survival. Efficient algorithms save time, memory, processing power, and massive amounts of server cost. This is exactly why software engineers are always striving to write the most optimized code possible.
Section 5. Tips for code optimization, winning the interview. Let's bring this right back down to your immediate reality with some actionable tips to dominate your next technical interview. Tip number 1 is glaringly simple. Avoid unnecessary nested loops. As we explored earlier, nested loops are the absolute enemy of scale. They immediately bump your code's complexity up to O of n squared quadratic time. Writing an unnecessary nested loop during an evaluation is honestly one of the fastest ways to fail it. Tip number 2, upgrade to efficient algorithms. Here are some concrete algorithm swaps you should memorize right now. For searching, ditch the slow linear search and use a binary search whenever your data is sorted. It cuts the search space in half every single time. And for sorting large data sets, replace the inefficient bubble sort with much faster algorithms like merge sort or quick sort. Tip number 3, use appropriate data structures. Sometimes the secret isn't writing a more clever loop, it's just choosing a better container for your data. For instance, if you need to search for items frequently, swapping out a standard array for a hash table can provide dramatically faster, often O of 1 constant time search speeds. It's a really simple change that drastically improves performance because you aren't scanning linearly anymore. Tip number 4, make optimization a permanent habit. Every single time you're finished writing a block of code, run through these 3 analysis steps. Ask yourself, can this operation be done faster? Are there any repeated calculations I can store instead of recalculating? And importantly, can I reduce the number of loops I'm using? And of course, practice. The more algorithmic problems you solve, the better you'll natively get at spotting these inefficiencies. At the end of the day, it all boils down to this. Writing correct code is important, but writing efficient code is what makes a great programmer. A slow brute force algorithm might work perfectly fine for a tiny input of 10 items, but it will buckle and fail completely under the intense pressure of large real-world datasets. Time complexity isn't just academic theory, it's the fundamental backbone of competitive programming and software development. So I want to leave you with this provocative thought as we wrap up this explainer. The next time you sit down to solve a coding problem, ask yourself, will your algorithm survive millions of users, or will it crash the server? Keep practicing, keep optimizing, and always be mindful of your big O. Thanks for joining me on this deep dive, and I can't wait to see you tackle your next big programming challenge.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to future BreaK Coder, because many exciting coding and futuristic tech videos are coming soon.